Welcome back to your stats course. Just as a quick review, at the end of Chapter 4, I made the point that it isn't good enough to simply summarize a dataset with a measure of central tendency. We also have to understand how the other scores are arranged around the central value, which in many cases will be the mean. This arrangement of scores around the mean is called variability. In this chapter, we'll be talking about measures of variability in a data set. For Chapter 5, I'll continue the practice of decorating the statistical lessons with abstract art from around the world. I hope to drive home 2 points. 1, I chose abstract art because descriptive statistics provide an abstract, distilled, simplified version of a set of numbers. And 2, for this unit on variation, I chose art from around the world to highlight the concept of diversity and variety. In this chapter, we'll look at abstract Asian art. Chapter 5 is going to cover measures of variability. Just as a review, in Chapter 4, we studied central tendency. Now we're in Chapter 5, we're looking at measures of variability, and in Chapter 6, we'll look at different ways of measuring the shape of your data set. In Part 1 of Chapter 5, we'll meet the range and a statistic called Q. In the second unit, we're going to look at variance and standard deviation. In Unit 3, we'll look at linear transformations. In Unit 4, we'll look at other properties of S, which stands for standard deviation. And in Unit 5, we'll have some closing thoughts on the topic of variability. In Unit 5.1, the objective is to define the following variability terms: range, interquartile range, semi-interquartile range, and then we'll have a rationale and an interpretation. When we study the interquartile range, it provides a foundation for understanding another statistic called the semi-interquartile range. The difference between the extreme scores in a data set is called the range. So the range is symbolized as R, and then the equation is symbolized as X max minus X min. And those symbols stand for X max is the maximum or the highest value in the data set, and X min is the lowest value in the data set. So the range is the difference between those two. Here's a simple example using the data set we've become accustomed to in prior lessons. The range is the maximum value of 10 minus the minimum value of 0. So the range is 10 minus 0, or 10. The range is the maximum value on this data set of 75 minus the minimum value of 0. So 75 minus 0 is 75. Is the range a good index of variability for this data set? When we look at this example, we see one of the limitations of the range as a measure of variability. We see that technically the data span a range of 75 scores, but is that a good summary of the diversity in this data set? I would suggest it is not a good summary of diversity because all but one score lives between 0 and 9. The range is very sensitive to outliers, and thus it's not a robust statistic for measuring variability. Recall, we covered the idea of a robust statistic in a prior lesson. If a statistic is robust, it isn't strongly affected by extreme values. Here we can see visually how the range gives a deceptive summary when the dataset contains outliers. If most of the data points lie within the black distribution of scores on this graph, we have two data points at the top and bottom of the distribution that pull the tails of the distribution out in both the positive and negative directions. It is these outlying points that will define the range. Thus, we get a deceptive picture of the range for the majority of scores. When there are outliers, the range is not the most useful statistic for describing variation in the dataset. The range is non-algebraic. We can't compute the range of a combined dataset with a simple algebraic formula. That is, we can't just add the range for group A, which has a range of 10, and the range for group B, which has a range of 4. We have to look at the two original datasets. We conclude by saying the range is a non-algebraic statistic. So let's look at this in some more detail. Assume you have two data sets, for example, two classes. And as I mentioned, the range for data set A is 10. So the difference between the highest and lowest score is 10 points. The sample size, or n, is equal to 50. The range for data set B is 4 points. So the difference between the highest and lowest score is 4 points. And the sample size for data set B is 30 children. So what is the range of the combined data set of all 80 people in the data set? So that would be 50 people plus 30 people, or 80 people total. So we see here that you cannot combine the two ranges with a formula. You need to look at the raw data. So we see data set A, which had a range of 10, ranges from 0 at the minimum score up to 10 as the maximum score. The range of data set B is 4 points. It ranged from 4 as the minimum score and 8 as the maximum score. So you can see that the entire data set B, all the numbers in data set B, are contained within the numbers of data set A. When we combine the distributions, we find that the range of 10, which was the range of dataset A, dataset B does not extend the range at all because all the scores in group B are contained within the range of group A. Whenever we can use algebra to make our work more efficient, it's helpful. We want to look at opportunities to use algebra in our statistical work. However, the current problem is not one of those opportunities. We have to do these steps without the help of algebra. This is a limitation of the range, and so we'll be on the lookout for a more sophisticated measure of variability, which we'll find as we move along in the chapter. So here we did combine data sets A and B, and we see that the range is still goes from 0 to 10. So again, data set B did not extend the range beyond what data set A already showed us. The interquartile range is somewhat more useful and sophisticated. It is the difference between the 75th and 25th percentile. Or we can also say the difference between the third and the first quartile. The range of the middle 50% of the scores, also called the H-spread, and we'll see why in just a minute. Here are the symbols for the interquartile range. Q3 to Q1 equals P75 to P25. So quartile 3 to quartile 1 is the interquartile range, and that is also symbolized as P75 to P25, so 75th percentile to the 25th percentile. Here's a visual representation of the interquartile range, and here you can see why it's called the H-spread. The graphic representation looks exactly like the letter H. And at the bottom we can see the labels Q1 and Q3, quartile 1, quartile 3, and P25, P75. So the 25th percentile, the 75th percentile, and here we see that 50% of the data points, or 50% of the scores, fall between Q1 and Q3. The interquartile range is a straightforward measure of the variation in the data, but let's refine our statistics a bit by taking another step and dividing the interquartile range by 2 to create the semi-interquartile range, symbolized as Q. So 1/2 of the range of the middle 50% of the scores is called Q. So we have Q3 minus Q1 divided by 2 equals percentile, the 75th percentile minus the 25th percentile divided by 2. Now you may be asking why Q is useful. The reason is this semi-interquartile range called Q has a nice property in a normal symmetric distribution. If all I know about the distribution is the median as a measure of central tendency and the semi-interquartile range as a measure of variability, I can compute the 25th and 75th percentiles. The median is at the 50th percentile by definition. We can add and subtract Q from the median to compute the 25th and 75th percentiles. So the rationale for Q in a symmetric distribution, we have the median plus Q equals P75 or 75th percentile. The median minus Q equals P25 or the 25th percentile. In sum, we can use the median and the semi-interquartile range to get a fairly good picture of what the distribution looks like. The usefulness of the median and semi-interquartile range as a way to get a feel for the data depends on a very important quality of the data. That is, it must have a normal or bell-shaped distribution. Remember, a normal distribution is symmetrical, and it is the symmetrical nature that is important. So we have median here, we have Q1, which is equivalent to 25th percentile, we have Q3, which is equivalent to 75th percentile, and then we have half of the semi-interquartile range we have divided into Q and Q. Here are the computations to find the first and third quartiles. So if you're given that the median is equal to 50, we can compute the median plus Q equals 60, or Q, that takes us up to Q3. If Q equals 10, then the median minus Q equals 40, and that takes us down to Q1. Now let's see if we can visualize that. When we take the median and Q together, we can divide the distribution into 4 equal parts. Each part contains 25% of the scores. It doesn't hurt to remind you that this rule depends on the scores being distributed in the shape of a normal curve, also known as a bell curve. So we can see we've divided the distribution into 4 different pieces, and we have 25% of the scores in each one of these pieces. So we took the median plus Q and the median minus Q. If you have an asymmetrical distribution and apply this distribution trick, it isn't helpful. The distance between the first and third quartiles is the interquartile range, and half this distance is the semi-interquartile range. But if someone only gives you the median and the semi-interquartile range, which is Q, and you apply this little trick of subtracting Q from the median to recover the 25th percentile, you will only get to the green line on the left end of the figure. The actual 25th percentile lies at the red line on the left side of the figure, so applying the little trick causes you to undershoot the first quartile. Similarly, at the high end, if you add Q to the median, you will get to the green line on the right side of the figure, when you really need to get to the red line on the right side if you want to hit the 75th percentile. So again, the trick of adding Q caused us to fall short of the 75th percentile. If the skew goes in the other direction, we get a mirror image of this problem. So the semi-interquartile range doesn't work with an asymmetric distribution. In sum, Q, which is the semi-interquartile range, is a useful statistic because it is a logical coworker for the median. By working together, these two stats give you a satisfying sense of the distribution, assuming, of course, that the data are normally distributed. If you're using the mode as your measure of central tendency, the range is a good coworker. These two stats can give you a sort of satisfying sense of the distribution. Admittedly, a lot of information is lost when you use these two stats to describe your data distribution. One of the strengths of Q is that it is robust to outliers, as is the median. Its big drawback is that it is a non-algebraic quantity. So I think you're willing to accept that the range and mode as two coworkers are somewhat helpful for describing a distribution, and the median and semi-interquartile range are a little more helpful to describe the distribution. If the distribution is normal, of course, that's an assumption. Next, we'll move to an even more sophisticated and precise measure of variability to go along with the mean, and we'll meet these statistics in the next unit. Next up is Unit 2 of Chapter 5, and we'll be discussing variance and standard deviation of the data. Mean, standard deviation, and variance are powerful workhorses in the world of statistics. So I hope you are ready to enjoy the ride.